Okay. 1 second. Okay. So welcome everybody. Today is week 14. We have been a long way. We've gone through a long way. We're going to talk today about how to model plasticity into OpenSees and STKO. Which kind of approach can we use? What kind of approaches can we use, and how can we actually put that in practice into some example models? So there's like two main approaches that are used to model plasticity. Let me see if this works. Nope. 1 second. Okay. So there's two main approaches that are used to model plasticity, especially in frame structure, which is to model it as a distributed plasticity or as lump plasticity. In the lump plasticity approach, there are two different types. If you lump the inelastic behavior in a finite length at the end of your beam or column, or if you do it in a zero length, so in a collapse point. So we're going to just talk about these three different approaches and how to actually model this kind of frame structure. As you can see, here's just a graphic representation. In a distributed approach, one way to do it is to use fiber sections, and fiber sections are distributed over the element in each integration point. Or if you're doing a concentrated plasticity approach, you have the same fiber section that describes the behavior only at the end of the beam at the two extremities. And so the plastic hinge has a finite length, or you can actually collapse the plastic hinge into a zero length. So without any physical length, any physical reference to the beam or the column. And this is true for 1D elements. If we have a distributed plasticity approach, so we use, as I said, fiber sections. So in a fiber model, the section, as you can see an example here, and all of its components are discretized into finite parts. Whenever you do a fiber section in STKO, you can see like a visualization of how many parts the section has been discretized into. For a rectangular fiber section, that discretization is, let's say, decided by the editor. But then if you do a custom fiber section, you can decide how many fibers you want to discretize your section. And then there's, in each fiber, you associate a generic inelasticity behavior, and you can assign different materials to different fibers. So for example, here we have concrete for the cover, then we have steel, this concrete for the cover, then we have steel for the bars, and then there's the automated generation of confined concrete calculations. So you can see here the unconfined value, the blue one, which is the same one that we apply to the cover, and then the confined value, the red one, which is the one that's going to be applied to the gray part. So the section response is the numerical integration of the contribution of each fiber. You can obtain stress and moment curvature coupled with the axial force. So this is very useful if you want to have a full description of plasticity along your element. And all the parameters for each section are integrated in the Gauss point using displacement and force plane elements. We talked about displacement and force plane element into our, I don't remember which number was it, like week 6, when we talked about element properties. So if you want to go back and kind of check out what's the difference between this type of elements, these two topics are quite related. But anyway, we're not going to discuss that again because we already talked about displacement and force plane column a lot. So today is just plasticity approaches. Anyway, the type of integration scheme that you assign to your displacement or force plane element would define how many Gauss points are there, and then how many in how many points the section parameter will be integrated in a distributed plasticity approach. Then if we go to a lump plasticity approach, we create, instead of a distribution of the inelastic behavior, we kind of collapse it into either a finite length, as in this example here, or a zero length, so a collapse point, which has no physical length. Plastic hinges are created usually at the extremities of the structure, which is where eventually inelastic behavior will occur first, and maybe that it will occur at the mid-span, but that's not normally modeled, the rest of the structure is defined as elastic, while in this location, specific elements are defined. So for a lamp plasticity approach with a finite length, you can define a fiber section for that finite length. Instead, for zero length, you need to define a phenomenological law to assign, let's say, a rigid spring with an elastic behavior collapsing that point. So it's a different way of describing an inelastic deformation. It's either through a uniaxial law that's applied to each of the fibers of your sections, or a phenomenological law that actually defines the behavior of a point in which all of the elasticity is concentrated. So in a final length, this plasticity is distributed over the length of the plastic hinge, yes, also said plastic length. In this case, in this space, we can consider the coupling effect of axial load and bending. And we have a nonlinear response available at the two ends of the beam. Now here, it's just been drawn at the base, but because this column was, let's say, free, but for example, into a frame structure, it could be useful to do at both ends. The elastic section at the beam in the center, so let's say in this part, needs to be reduced in terms of stiffness, because otherwise you're not going to take into account the cracking due to bending that can occur in the center of the beam due to the deflection. And this stiffness reduction has to be in terms of inertia and not in terms of area, in order to be able to, let's say, not shrink the section that we have, but trying to match what is a real inelastic response of an element like this. We are going to see later better how this can be achieved. In OpenSees and STKO, this is modelable. I don't know if you say that. You can model this through an element called an element and a physical property called beam with hinges. This is an error that a lot of people do. They create beam with hinges physical property, and then they assign a force beam column element. So just remember, everybody, that there is a beam with hinges element properties, and that's necessary to be assigned to a beam with hinges physical property. They need to go together, otherwise your model will not work. A beam with hinges element property is not other than a force beam column element with a different integration scheme. So you can choose among the ones that are available, and there's a lot of literature. You can go read about how and why, for example, the Injur-Dow integration scheme can be useful and used. In this case, for example, it's quite used because you can specify the length of the plastic hinge, and that will guide the localization on the first integration point. So you will have the result exactly where you think the localization will happen. And it's not going to be it's going to be a result at an integration point and not along the element, which it's less exact. So going forward, just for you to know, this is the kind of simplification that we do with a finite length plasticity approach. So imagine that a full inelastic approach is a full yellow curve that follows an inelastic behavior, starting from, of course, an elastic one. And then we kind of simplify the first portion of the behavior, moving on to a plasticity when the localization happened at the bottom or the top of the beam. I don't know why okay. Then if you want to move towards a zero length approach, we can see now that the graph changes, because what we did before, it was applying a specific stiffness to a finite length. But now what we're doing is applying that stiffness into a collapse point. What we're going to say is that that point is almost infinitely rigid, but of course that's not possible to do numerically. So we will have to kind of just define a very, very large stiffness for this branch of the phenomenological law. And we have to define, of course, a phenomenological constitutive behavior, no more into moment curvature terms, but into moment rotation curves, because we are assigning this to a point. A point does not have any curvature because it's just a point. In this kind of approach, we don't have any coupling between the bending response and the axial response. So this is just going to give me when the localization will happen a fracture in that point, but not a fracture, let's say a failure in that point, but we will not see an inelastic behavior that can spread out and that can couple the two responses. So just to sum up what we said until now and adding a bit of more things to compare these two approaches. With a distributed approach, we have an automatic integration of the PM response, and we can also introduce shear. Instead, with a lumped approach, we have a coupling in the finite length if we use a finite length, but otherwise, if we have a zero length, we have no coupling. The inelastic behaviors there is distributed along the element in the distributed approach, or lumped in a finite length or a zero length, collapsed in a point. Of course, there's like, why you would say, well, why would I want to use a lumped plasticity approach given that my inelasticity or my plasticity is not represented like correctly, or let's say more realistically? Well, these kind of approaches are much more efficient computationally because you have less, I mean, to extract result in each fiber is very heavy, computationally speaking, expensive. So to do a distributed approach, it's feasible if you have models of small dimensions, or anyway a small size. Instead, if you want to be more efficient, and anyway, if you're not really interested in knowing what's happening at mid-span in your beam, then you just want to, let's say, model that plasticity, but without going too much into detail. This is the approach to go to. LAMP, this is the approach to go to. And also there's another advantage, because if you're trying to reproduce an experimental behavior, for example, and you want to use the distributed approach because you don't want to compute your own phenomenological law for the spring, but then this type of inelastic behavior is defined by the response of the fiber, which is guided by the type of uniaxial laws that you define for the materials. And first, you could get those wrong, and second, you cannot include so many things into an uniaxial material law. Of course you can, because for example, there's the hysteretic material, or there's other types of material that you can actually describe any curve that you want, that you have obtained, for example, from your experiments. But then it's quite heavy to do that, to kind of calibrate the way, for example, an hysteretic or a pinching floor curve works if you want to include, I don't know, bar sleep or buckling or any kind of other effects that you have experienced into your experiment. And so if you have a specific curve that you just want to linearize and reproduce and apply to a spring, that's also quite like immediate to just include it into a zero length and apply it as a lumped plasticity approach. So we have an example that was already discussed by Massimo in another course. So I did not invent anything. I just took back his material, and you can also find this into a much longer webinar on the website. So what they did to compare these three approaches was to create a column subject to axial loading and fixed at the base. First with a fiber section, so with a distributed approach, distributed all along the element, then with a plastic hinge and finite length, and then with a plastic hinge in a zero length. There was also some other, let's say, some other operations that he had to do to be able to reproduce the behavior of all three beams into something that was comparable. So if you see here, let's say the continuous curve is the distributed approach, then we have the red curve that follows that distributed approach is the finite length one, because with that kind of yes, distributed but lumped kind of inelasticity, we can still capture something that is more smoothed. And then we have the linearized curve in pieces obtained with the zero length approach. As you can see here, the fiber sections are in each integration points in the distributed approach. In the finite length, they are at the edges, and then in the zero length approach, there is no fiber section. So this is explained into this model, example 18, that you will find on the website. I just wanted to point out that, I mean, we talked last week on how to calibrate these kind of parameters. So how to build your your concrete and your steel and also hysteretic materials or pinching for materials. We discussed, I don't know if we discussed rectangular fiber section, maybe we can do it a bit now. So there is this editor that we developed in STKO, in which you can actually define customized rectangular fiber section by applying both dimension, reverse configurations and dimensions, materials, and also transversal reinforcements and offset. And by just like not applying the core material, there will be an automatic calculation of the confined concrete given like one of these pre-selected confinement model. So you can also change the confinement model with another one and obtain the one according to, for example, specific regulation rather than maybe the most common one, which is Wander and others. If you do assign the core material, so if you go here and you do assign the concrete, you see there will not be any automatic confinement calculation. I know this is not very intuitive. I was asked many times, how do I do the automatic confinements? Because also it doesn't say anywhere. We should add like a little note here. But yeah, so this is how you do it. And just remember, every time you're working in 3D, you need to assign GJ to your fiber section, otherwise your model will not run. You will have an error in the force bin column element. So to model the distributed approach, what we do is just inserting this fiber section into a Lovato integration scheme and applying it to the beam. Then if we want to go forward and apply a finite length plasticity approach, we're going to reuse the same fiber section for the plastic hinge because I mean it's the same, but for the mid section here we're going to use an elastic section. So instead of the standard integration type here, we can use the hinge type, and with the integration type hinge rundown, you can define the length of the plastic hinge and specific section tags for both the I don't know why this one, it should be this one. Okay. Oh no, you're right, I always make this mistake. Just remember, the first two are the extremities and the last one is the mid section. Also, this doesn't say anywhere, but anyway, I and J are the two nodes at the extremities and E is the middle section. So in this case, to reduce the elastic properties of the mid section, because otherwise the response would have been too rigid, we applied a stiffness modifier, which actually scales the bending stiffness around the local axis theta of, for example, 35%. 35% is the number that experimentally is like provided, that you can say that distributed approaches and lumped approaches kind of match. But you can also make your own experiments with this number and make your own literature review and see if there's a better number for your own specific model. So this is not like a given rule. And then this kind of property can be assigned directly to the beam, and we have our finite length plasticity approach. In order instead to build our zero-length plasticity approach, we have to construct the phenomenological law. So this can be sometimes daunting because you don't know where to start. One thing that's like very common, if you have, for example, a large structure, but you have some typological sections, what you can do is model those sections small and make this kind of experiment, this kind of model, simulating what's the moment curvature response of a single column with that type of section, and then extract moment curvature response of that column and use it to calibrate the spring parameters. So we're gonna provide you with this Excel utility. Let me show you. Sorry, desktop. Here. Yeah, this one. Okay, so here we have, I'm not gonna go through the actual calculations in this thing. I have a slide for it, but just for you to remind, this is a just an example of how you can do this using the modified Ibarra-Medina-Krawinkler deterioration model, which is available in OpenSees. So it's this material here that can be used for defining your spring behavior. So I don't know if this is set well. Let's try. It's too long, too far. 0.1. Yes, okay. So if you can see, this kind of matches the moment curvature response that we have for our distributed approach. I'm just going to show you very quickly what kind of results you can get. I set up an output. This was for later. So, for example, this one, okay, this one is our moment curvature response. So I extracted at the Gauss points, at the bottom here, I extracted the curvature kz, and then at the node here at the bottom, I also extracted the moment reaction in the y direction. And so putting those two things now, I copy pasted the values from this graph to this graph, so you don't see anymore the time here as it says, but it actually says this is the moment curvature response, of course flipped because it's a negative moment. And so this kind of information can be used to calibrate the spring that I want to apply here. So I know that my plasticity behaves like this, and I want to reproduce that kind of behavior on a zero length. So how do I do that? So first, the first step is to bilinearize this curve, trilinearize this curve. Actually, you can also bilinearize it. It's just your choice. You don't have to use a trilinear type of behavior. So the first is to trilinearize your choice. So kind of define where is it that your curve is moving and like changing direction, and saving those points as guiding points of your behavior. I have here. This also can be done, for example, with a pinching for. It doesn't have to be done with a modified Ibarra-Medina-Krawinkler model. So if you want a 3-point backbone curve, or if you want a 2-point backbone curve, you can choose. So it's your own decision. And from this trilinearization, what is there to do is to move from, let's say, our total curvature to the plastic curvature. So we want to extract the ones that is like the elastic part of the curvature and save just the plastic one, so that we can apply that to the spring. And to do that, we're going to divide. You can just divide the moment of these points. So the reaction moment that it's applied in these points by the initial stiffness of your curve, and then you obtain a kind of plastic phenomenological behavior that it's infinitely rigid here. From this point to, because of course, if you divide here for the stiffness, this is the initial stiffness, you're just gonna get the initial point. Then if you want to move from here to what you have to actually apply in the spring, you have to move from a moment curvature diagram to a moment rotation diagram. Because as we said, a zero length is collapsed, so it has no curvature. We cannot apply a curvature phenomenological law to a point. So to move from there to here, we just are going to multiply our plastic curvature for the length of the plastic hinge that we hypothesize that it's the length in which the localization will happen. And we obtain a moment rotation curve. Then we need to regularize this curve because, of course, here from here to here, I don't know, this is not appreciable. You cannot appreciate this through this graph because they are kind of overlapped. But you need to regularize the response, because otherwise you will have an infinitely rigid initial response. That's not something you can model numerically. You have to just move this point a bit further. And in this Excel file that we give you, Massimo defined this regularization to be applied to all the points. But I mean, you can just regularize the first one. You don't have to do it throughout the whole curve. It's just your choice. And so to do this, the regularization actually will just move the initial point of, let's say, a couple order of magnitude higher than the initial stiffness, or something like that. For example, this is the initial stiffness, K0 multiplied for 100. So 2 order of magnitude higher than the initial stiffness. And with this initial stiffness, you can use it to regularize the initial rotation to a regularized rotation. So that, I don't know, in a way you are getting, let's say, a response that is not infinitely rigid, but much closer to that. And so with this kind of points, I mean, in the modified variable linear model, you don't have points as you have in the pinching 4. So in the pinching 4, you have exactly the coordinates of the point that you have to input, and those coordinates needs to be just defined in terms of stress and deformation, in this case, moment rotation. But in this case, in the case of a Barra-Mendel clavering, there's some calculations to be made, and we made them for you, so you can just check them out and see how to calculate actually these coefficients. And there's also a lot in the literature, so if you just move from here to the OpenSees documentation on the Barra-Medina-Craving model, you will have, sorry, I don't know why this happens all the time. Let me move this to another browser. Yeah, let's move to another browser. So all of these values can be found in the references here, and also the equations to calculate them. Also, you can double check what we produce. So, I mean, if you found that you need to use this for your models, then please do double check our calculations so that we are sure that we are actually giving out valuable information to people. And so this kind of spring can be used inside of a zero-length material. So in each direction I mean, in this case, we want to model plasticity just in the rotation around Z, because we are actually imposing an axial load, and so we want to see the deflection in that caused by that load, and that is our inelastic response. But of course, you can have an inelastic response in a different direction. And so first we define the stiff material, which is just an inelastic material with a very high stiffness, not too high, because of course you will have like ill condition problems. So please do not just like go and write 1 to the power of 45, because that's complicated. But and then those 2 materials can be inputted here in the zero length, and you can assign. Of course, now we are in 3D, but if you're in 2D, you can use less directions. And as for the lumped finite length, for the lumped zero length, we include the inch at the edges, but not anymore into a beam section property with an inch Randau integration scheme, but we can use an inch beam physical property. This inch beam physical property as the same as for the rest, you define an elastic section and apply a zero length at the 2 extremities. And for this kind of section, you need to use an inch beam, also element properties. So as I said before, the hinge beam element property is none other than a force beam column element, which gives you the possibility to assign zero length at the edges, at the extremities. And that's it. I mean, this is a simple analysis, a simple horizontal analysis. A simple vertical analysis with a prescribed axial load. And this is the response that you get for all the 3 different type of approaches. Of course, here we don't have an integration points because we did not apply an integration scheme. Instead, here we have Gauss points and results of the Gauss points. what I can show you more on this topic is just another example that I have, that I put here, that you guys can just look by yourself. This is just a frame structure. We call this the little table here that we've used over and over again. And for example, this is just for you to see that you can use combinations of these two approaches in the same frame structure. So you don't have to use to make all the beams and columns with specific plasticity approach. Sometimes it's even like useful to model plasticity only on the beams as distributed, because you know that the columns will work in a kind of a different way. I mean, it's depending on the type of analysis that you're doing and the type of loads that you are applying. So it will just be a modeling choice. But as you can see, for example, here we did distributed approach both for columns and beams. Then here we did lump with finite length and distributed on the top. And then here we did lump with finite length at the top and lumped with zero length at the column. So you can find these files. I will give them to you with our support files for this week. Sorry if I was a bit like slow, but I don't know. I mean, we are in the time anyway. So for each of this file, there is one of the three approaches. Starts with the distributed, and this is, for example, the final length approach. And you will see the application of the same materials there. What you can do as an exercise, if you want to understand how this works, is if you have a large frame structure, you can take the sections and make some small models like the ones that I showed you before to extract the Morvan curvature response of that type of section. And so calibrate your phenomenological law in the spring in order to be able to apply a finite element, a lumped plasticity approach. So thank you for participating today. Let's see if anybody has any question. I've seen there's someone who kind of got in right now. I'm sorry that it's been, is this like Kastub? He's connecting with the audio, so he cannot answer. Anyway, while it's connecting, if any of you four has any questions, we can go for it.
Okay. I have three questions. The first one, when we speak about the lamp plasticity zero length, we said that we need always to define the hinge beam property and the hinge beam element.
Yeah.
And both apply to the node.
No, to the column.
Sorry, to the element, to this element. But then, because I think I like if I see the file, then I will, when I study the file, I will understand. But then in this same zero length element, we have, apart from the hinge beam property and element, we have also the elastic property, right? Because we have the stiff property.
You don't need an elastic element property. You just need an elastic physical property, because you're saying that it's, I'm going to show you. So you're saying
I got lost. Where we input this elastic property? So
we define an elastic section that, for example, is the same as our fiber section. With in this case, we didn't do it, but we can apply a modifier that lowers the stiffness. And then this elastic section, we're going to go and say our beam is the elastic beam. Okay. And then our zero length are these two at the edges. Let's open the other file and see.
Okay, so when I define the hinge beam as a property, there I say which is the property that is going to rule my zero length.
So when you define an hinge beam as a property, you need and a property for the whole beam. So something that you want elastic, you know that it's going to behave elastically because you're actually lumping the plasticity in the zero length. Then you need a zero length material in order to assign the spring in the direction that you want, and then have a rigid behavior in the other directions. And that's it. So you need an elastic section, these two type of materials.
Okay, now I understand. In the zero length, I apply the elastic, the uniaxial elastic, and the molding pinching. And then when I define the special purpose pinch beam, there I take this last zero element. Okay. I wasn't able to see the connection. Okay, now I understood.
Into your beam, and this is gonna be created automatically. You don't have to assign anything to the node.
Okay. Oh, no, this was like, because I wasn't seeing where the elastic property was, because we were saying one part is elastic because we collapse everything in the extremities. So I was
not saying something correct before, because you do need an elastic beam column element for your beam, and also a zero length element. So the hinge beam here is created the same. Of course, you don't have to reassign the uniaxial property or the section, because it's just an element property, but still you do need the property for the zero length and a property for the elastic. You could also have used here a force beam column element here, no problem. Like there's no difference. And then because of course you have the elastic section, so it's gonna be anyway elastic.
Okay.
And then outside in the hinge beam. Next question.
Yes, and the next question was, again, because you were opening the fast. Then when I study the file, and then I can, because you know that you have to like go, you create one and then you put it in the other, and then you put it in the other. So in the case of the other, the lamp plasticity with the finite length, how do you define the length of where you are going to concentrate everything?
So if you have a normal distributed approach, you have standard integration type. But then if you want to define the length of the plastic hinge, you use a hinge type of integration with the hinge and down one. And then you select what you want. Of course, this is 2 up, so I cannot do it. You select what you want to see at the extremities. So I want the column fiber at the extremities, and I want my plastic hinge length to be 150, because I also know that that's the distance of the integration point in the hinge and down. So it can be useful to have the result of the Gauss point at the same level of the fiber section, because that's where I know the localization will happen. And then I select something for the core of my element here. So yes, you do have to nest physical properties in this case.
Yeah.
To achieve what you want.
Okay, no, I was taking notes and I didn't see where did you put the length, and I was okay, maybe it's nested somewhere else, but I wasn't. But okay, everything is in the beam section property. Okay. The last question: when you say that, for example, you can do a small, like let's say you have a whole building, and you don't want to do the distributed plasticity in all the beams, so you go to a small one like this small table, and you calibrate like this beam.
Mm-hmm.
Then
you calibrate the phenomenological law for the spring.
Exactly. So I can like do this small table and calibrate the phenomenological law for the beam, and then I can do these springs and use this from like the really simple one to the big one, right?
So the idea is that you want to know how your section behaves in terms of plasticity, no? So you can have a unitary length in your beam. For example, in this case, I was to show you this that Massimo did. In this case, he's using not a column, but it's just a section. So he has a fiber section that is just of a unitary length. So I think this is like very short. It's just one or something. And then in this kind of, I'm just gonna go a bit forward. Yeah, you see, he's just extracting the result because it has one integration point, so one fiber section. And from here is extracting this moment curvature response. So you can either do this or have a column of a length that you know what it is, and you can scale it up to the to your big model. But I mean, also if your column is 1 meter, it should work the same. So it's just you don't need to have an axial response that depends on the length of the. Sorry, you don't need to have a moment curvature response that depends on the length that you are actually using. So the column has to have one length, a 1 meter length, or 1 millimeter, whatever. And with this, you can calibrate the spring that you want to apply in the lumped plasticity approach. So, but also this is also a good approach. So there is also this model here. If you go to this website, it was like very early on, but it's called plasticity. And you can also define this kind of section, extract the moment curvature from here and use it into this kind of calculation, also do them by hand to use another type of phenomenological, another type of physical property, for example, the uniaxial pinching force to define your backbone. Maybe you want to.
I can use it to obtain the phenomenological law for shear, for example.
Yes. Pinching force is theoretic, you don't do it for shear, yes.
Great.
In that case, if it's length, it will be not a shear display, not a shear deformation, but a shear displacement. Shear displacement, like shear ratio, shear drift, and then shear.
Okay, thank you.
I don't know if anybody else has any more questions. I'm sorry if the last Kautzbu, sorry, your name is very complicated. That you joined very late. So just for you to know, you will find the recording on our website. I will say this all the time, but so if you go on our asdesoft.net in the training session, you will find the recording over here. It will be here by tomorrow. So I'm sorry that you joined in late. Just for everybody to remember, it's just an half an hour conversation and some questions time. So if you want to participate, come on time. Can I ask Matilde, what is it that he's going to model in his PhD with OpenSees and STKO? And also if Antonio or Jimmy have any questions or anything that they want to share, any models that they're working on, that's also welcome. You're a novice, okay, but then you're in the right place if you're a novice, Antonio. This is exactly where to start. Good. Okay, well, just given that you're new, I'm just gonna share this other thing too. We have a forum in which a lot of users post their questions. So if you go on our website, support. I don't know if we ignore the last post from Larissa. I don't think so.
No. Everything was answered and everything is running now. So I will have other questions, but that will be for next next week.
So yeah, we have new posts here that I haven't seen today. So just so you know, here you can just register as a user and post some questions, and we will answer. We answer very promptly. So okay, so you guys are welcome, and I hope I'll see you next week. If there's no more to add, I can share with you the files in the chat if you want, but I don't think, no, I will just upload them tomorrow morning. And thank you for participating.
Thank you, Francesca.
Larissa. Ciao, everybody. Hi, bye,
See you
Maite.
Wednesday. Bye bye.
And bye, Antonio. Bye. Bye-bye.